for you to watch it later. Okay, and then let me share PowerPoint. So we already went over the requirement for the next stage of your project. Okay, so now you have like 80%, 90% complete hypothesis. Okay, but I want to leave like a 10, 20%. By deciding or picking exact variables from the secondary data set. So there's room you can still modify the part of your hypothesis. But next stage, and also due for next, not this, but next Thursday, is the variable cleanup, variable description. So I expect you guys to do 4 different things at this stage. Okay, with each variable, whether it is independent variable or dependent variable, what I want you to do the first, okay, describe your data set. Second, okay, now it's starting cleaning variable. So if the variables are mostly from GSS data set, it is coded as it's supposed to be. And in more ordinary way and more clear categories, just you can keep the original variable, but sometimes it's not. You're supposed to recode them to do actual analysis. So that is actually the following stage of the project. But at this stage, clean the variables, okay? And then I want you guys to have this hypothesis operationalization table. So what that is, just for you to organize it, it's gonna be the part of your really report. I want you have list the number of and the exact dependent variable and exact numbers and then specific names of independent variable, and then from which data set, ANS data set or GSS data set, and then making sure the important thing is measurement. Okay, so whether it is originally coded, one is male and two is female, just put it down there. And if you recode it or like reverse coding from, strongly disagree as 1, strongly agree as 7. Just put that down as ordinary. Okay, so maybe we can decide that we're gonna use as a nominal variable or interval variable. So I want you to just make hypothesis operationalization table, and then you come back for each variable. You should run descriptive statistics with the frequency distribution table, which we already practice, but that will be the each of your hypothesis, at least a couple of them. I want you to do with me this coming Thursday. Okay, so after I show you what you're gonna cover today and then part of the beginning of Thursday class, correlation test and regression model. After that, and I show you how to run those model and those statistics with the SPSS software. And we will go over at least selected variables for your hypothesis. Okay, so having that in mind, just bring your variables. Okay, so at least for rest of the time, at least one variable for each of your project. I want you to go each step and in part of the hypothesis operationalization table, and also you can work over a week, and then next Thursday, okay, so we do at least a couple of them. So over a week, you complete for the rest of the variable, and then before before the actual submission, which is due next Thursday, not this Thursday, but next Thursday. And I wanted to make sure on that Thursday you probably done. And if there's any final questions you have, and I want to answer that, and I want to help one-on-one on that. So just to bring something for this Thursday practice. You got that? Okay. So this week, it is the first time for us to move uh, for statistical analysis, dealing with only interval variables. Okay, only interval variables. So both whether you really think about which one is independent variable, which one is a dependent variable, regardless, they are related, they're correlated, or they are more close. In fact, regardless, if you are dealing with only inner variables, that's the analysis we're gonna look at starting this week and part of next week and the following weeks and as well. So when we are dealing with only independent, I'm sorry, two, at least two inner variable. So that's the statistic area and the roadmap area where we are. So in other words, whether it is independent or between different just variables, you only have numeric and inner variables. What kind of a test you can run? Okay, so of course, in order to decide whether it is going to be a correlation test or it is going to be more of a regression test, it goes back to your hypothesis and scales of measurement and all that. So you need to decide whether it's a correlation test or regression test, depending on your hypothesis. Okay, but in terms of the scale of measurement, both correlation test and regression model, they have all interval numeric variables. You got that? Okay. So that is why it's important in hypothesis or polarization or table. If you're independent, both the variables are inable, then you automatically come down. Oh, so it's right on the right side of the statistical roadmap. So you know where you need to go. All right. So let's talk about correlation test. This test analyze relationship between so between two inner variables. So how they are related. Okay. So your hypothesis is whether they are positively related or negatively related, whether they are strongly related or weakly related, or whether they are linearly, straight line, linearly related, or maybe they are different form of a relationship. Okay, so your hypothesis is related to direction of a relationship, strength of a relationship, a form of a relationship. You can use a correlation test as long as your variables are inner and quantitative variable. Okay, so that is hypothesis and scales of measurement for the correlation test. Okay, moving along. So let's use the examples of a correlation test. Okay, sometimes you can already predict causal relationship. Okay, excuse me. I almost sneezed. Okay. And but sometimes you don't really want to have any assumptions that what causes what, right? So for example, you just simply your hypothesis is that the beverage temperature is related to the temperature. Okay, the consumptions of hot and cold beverage is related to the season and temperature. So usually it's some market research found that cold weather it really increased coffee consumption, hot tea consumption. And the weather gets hotter, people like to have like a colder beverage, like a cold icy beers. But I had my PhD degrees at a University of Florida, but Southern University when we have like a tailgate party for the football season, when hot summer, when the temperature is really high, and if you drink a beer, body temperature will go up. I don't know whether it's really health wise. It's a good decision, but anyway, it just kind of with this satisfaction that it's cool and icy cool beverage really help with some more consumption during the summer. So if these are something what you are looking at, This can be confirmed by correlation test. Okay, so for example, we can decide the correlation test can tell you it's possibly related or negatively related. That's what they can answer, and also they can answer how strongly they are related. Okay, so as you see, can you tell which correlations is the strongest and which correlation is weakest here? A, B, C, D. Which one is the strongest?
Would A be the strongest in a negative
Yes,
correlation? Okay.
exactly. So it's negatively correlated. It's the strongest because it's tied up and it's one line is straight. So that is the strongest. That's a correlation test. Tell you the value. Tell you how strongly correlated. As you see, maybe C is a better correlated. Okay, it's a possibly, and D somebody to weakly. But I see it's maybe negatively related. And but D, I mean B, I don't know if there's any correlation is going on here, right? So by this scatter plot, and we can tell the strength of and the correlation value tell you the strength of the correlations. Okay. And then the last part of the answer you can have from the most when we hear, okay, this is a correlation test. 99% is a Pearson correlation test. So what they are measuring is a straight line. Okay, if the straight line the values are high, it's how strongly they are correlated at the straight line and linear relationship. Okay, so some are like a curve, some are like fluctuating. They will have a weaker Pearson correlation value. Okay, and then you should maybe utilize a different analysis. Okay, maybe sometimes you divide the different range to run different correlation tests, or maybe you can use other multivariate tests having like an intercepted point and then run different model. But when we look at the correlation tests, most of the correlation tests you see from the academic work, the Pearson correlations, it is based on the linear relationship. So when the correlation values are high and strong, that come from that, it is just linearly strongly linear relationship was strong and solid. Okay, so let's talk about the Pearson correlations. It's the most common correlation test. Okay, they looked at degree and how strongly and direction of a linear relationship between two interval and continuous variable. Sorry about I'm saying interval variable, quantitative variable, and continuous variable. It's all the same thing, okay? But different statistical textbook and sometimes a different article, they just use this term interchangeably. So I just try to expose you guys to the same thing with a different term. That is it, okay? So Pearson correlations with the statistical notation, we use R, small letter R. What they are actually measuring is that how. So here, do not forget, so don't think about x and y. Usually, x variable in statistics we identify as independent variable. Y usually as a dependent variable, but forget about correlation in correlation test. Whatever variable in x, that's what it is. I will tell you the limitations of correlations and benefits of regression models. That is all about the causal relationship. So wait for that. But correlation tests, we don't care which is independent and which is a dependent variable. We just look at whether there is a co-relationship between two variables. So what correlation, Pearson correlation are measured. So two interval variables, how much their variability changes together, okay, correlated versus, which is mostly error in denominator, divided by uh, how they really move separately and randomly. Okay, beyond and deviated from the sort of patterns they are moving together. Okay, so that's Pearson correlation test. Okay, whether those two variables moves together, that's the numerator. How they are moving randomly and separately, deviated, that's the denominator. Okay, so hypothesis wise, again, hypothesis, we always use it for notation for population, right? We use a great letter rho. Rho is equal 0. So that means it's just a flat. And your variables, however it changes, it doesn't matter, it's just a flat. Okay? Then there's no relationship going on. The alternative hypothesis, what we actually wanted to confirm, they're related weakly, negatively, or strongly and positively, whatever it is. We want to detect some sort of linear relationship. Okay, so the rho is not zero. That's alternative hypothesis. If you wanted to write hypothesis with these notations, or as I mentioned that earlier, you can state your hypothesis in plain English, no problem at all. Okay, variable A and variable B is correlated. That's your alternative hypothesis. There's no correlations, or any relationship between A and B variable. That's null hypothesis. Okay, so this is a scatter plot. You can see how correlation values goes along with this scatter plot and the relationship between like variables. So let's say this is a sort of x and a y graph. Okay, so when you see some random scatter plots like that, whichever the x variable y variable goes, we can really see any pattern. The correlation is zero. Okay. And then let's see, maybe right here, it's more consistent, but it's negative. Then correlation value is negative, and then it's a zero point 0.7. Let's look at this. The negative and the correlation, actual correlation value for this scatter plot is 0.99. So having these values as scatter plot, can you guess what might be the maximum values of correlation and minimum values of correlation? What is the maximum value of correlation value R can go? And what is the minimum correlation values can go?
Would the maximum, I'm sorry, would the maximum value be 1?
Yes,
Okay, and then the minimum would be -1.
that's exactly,
Okay.
it can be confusing part. Okay, so look at this. It's a negative, almost -1, but it's a strong correlations, right? So yes, you're right. In terms of the numeric value, -1 is the smallest one, but actually in correlation tests, I'm glad that I asked. A correlation test, the maximum value of correlations are +1 and -1. Okay, because they're strongly correlated, but minimum value of correlations can go is 0. Okay, so that's how you can understand it. So although it's negative, it's a strong correlations. Okay, then it's a maximum correlation value. So, but the good thing is that because we have a negative and positive value, that really indicate the direction of a relationship. We oftentimes are very curious about in many real world research. Okay, great. Thank you, Dylan. All right. So again, I'm not gonna ask you to calculate it or just to put, just insert numbers and just to do, find the statistic value. But I want you guys to understand that what really correlation value are really assessed, what they're dealing with. Okay. So here, correlation value really use three different numeric value. standard deviation for first variable, and another standard deviation for the second variable. It doesn't matter. You're gonna put standard deviation of x variable as numerator and denominator. It doesn't matter. But you just put the ratio of standard deviation of two variables, just like that, and then multiply it by the slope, which is a slope means by, when one variable changes by 1 unit, how many changes in the other variable, right? So in other words, maybe 1 unit changes in x variable and how many unit changes in y variable. That's slope, right? So basically, Pearson correlation value is calculated by the ratio of standard deviation between two inner variable multiplied by the row slope. Okay, so that is the Pearson correlation value. So, in other words, okay, somehow the slope itself, we use a standard deviation to standardize the slope. So, oftentimes, some statistic textbook, they call the Pearson correlation value as a standardized slope, standardized versions of a slope. That means it's a Pearson correlation value because there's the row slope and we multiply with the ratio of standard deviation. So we make this slope standardized. That is why we have the range of from -1 and +1, 0 being most least correlated, and +1 and -1 is most correlated, maximum correlated. Okay, so that is a Pearson correlation test. So let's talk about the properties of the Pearson correlation. So valuable correlation value, the valuable correlations, they are independent. In other words, not related to variables unit, okay, because it's a standardized using the ratio of standard deviation for both the variables. Okay, so they are not really just depending on the unit of analysis or what is the scales of measurement. We already standardized with the standard deviation of those two variables. Okay, and also correlations are symmetrically related. So when you have a correlation value calculated, you can say x is related to y, that correlation value, and y is correlated to x with that amount and in at that degree. So you can put either way. So the symmetrically interpreted and also symmetrically related. Okay, but important part of understanding of Pearson correlation values, it is a standardized slope, which is just really different from the slope for the regression model. So just remember our value, correlation value is a standardized slope. Okay. So, but when we actually come down to interpretation, it's a quite cumbersome. So, if we use the correlation value itself, you can like interpret if your one of your x variable or one of your variable increased by one standard deviation. What's happening to the other variable? That's the or increase or decrease of our standard deviation. What? Okay, so standard deviation itself is a quite cumbersome, information. It's like average distance from the mean, but you select a random number, and then if you want to put that in the interpretation of correlations, it's quite awkward. Okay, so we actually use not the raw value of R, but we use a different number and using R value, so that I will go over soon. But the important thing for you to remember is that Pearson correlation value is a standardized slope. It's the same thing. Okay, so continuously, -1 and +1 is a perfectly linear relationship. And absolute value of R value, regardless of the sign, negative and positive, regardless of sign, if the absolute delta value of R is larger, then it's more and higher degrees of correlations. Okay, that's how you can think about. Okay, but I understand that minimum number is anyway it's -1, but it's actually negatively related, but maximum correlations can go to the negative direction. That I want you guys understand. Okay, so I want you guys just to see um, some issues related to some limitations, or sometimes it can be strength of a correlation test. Okay, when you have a hypothesis, really measuring causal relationship. So if you identify in your hypothesis there is an independent variable versus dependent variable, then forget about correlation test. Okay, correlation test, as what we talked about, they don't assume causal relationship, just they're related. If your research question is only about the relationship, whether they're related or not, perfectly good with the correlation test. But if you want to go beyond just to see some of the causal relationship, you should use regression model in place of a correlation test. Okay, so causal relationship is not part of correlation test. Okay, and then also let's think about the range. Okay, so let's say for correlation tests, you should be very careful considering all those theoretical and practical matters. Let's say, there is some linear relationship across the variable A and variable B. They have a linear relationship, but somehow you ended up with like a small range of the group, and look at the relationship. Although they are linearly related, okay, correlation is strong when you wide open to just a bigger range. You can find it, but if you narrow down to the smaller range, maybe among that short, small range, there might be no relationship at all. So the range is a very important and sensitive thing for correlation tests. So when you do correlation, make sure that whether you're gonna really cut, for example, age from 29 to 40, may you don't see any correlations at all about just the media uses for political communication. But if you extend the age group from like a 15 to 99, okay, or oldest person in United States, then you clearly see the digital media consumption and conventional media consumption. You can see some pattern, right? So then correlation makes a lot of differences. So you should be very careful what range of the variable you are gonna look at. All right. And also outlier, it's big problem for causal relationship. I'm sorry, correlations. Okay, forget about. I want to take it back. Fully take it back to causal correlations. So when let's say the linear line, okay, between variable A and variable B, it was like it just weakly related, but somehow one outlier right there, one in a high and very steep, and it really make this correlation line much steeper. Okay, so it's leverage of the correlation line. Okay, and these outliers, they really change the correlation value dramatically. So making sure that if you have maybe really not important, unnecessary, big outlier, it's better to leave it out, okay, for correlation test, because that one case or that one score can dramatically change overall correlations, okay, that are dramatically different from the rest of the correlations among the data or data score, okay. And then I talked about interpretation, okay. As I mentioned that our value is okay, how much changes in a one variable A, one standard deviation changes in variable A, that's our standard deviation where changes in variable B. No one can really get any intuitive understanding of what that means. Okay. So when you write up the result with the correlation test, okay, report R value, which is like whatever the value you can come from the correlation test, and then provide the sample size. And then you have a exact p-value from the distribution, each distribution table. And now I'm just since the manner of reading, just finding the specific scores. Okay, um, I do not want to repeat. Okay, but as long as your probability value, okay, it's less than 0.05 or 0.01, that means it is statistically significant, rejecting null hypothesis and accepting alternative. In this correlation test, alternative hypothesis is these two interval variables are related. Okay. But we wanted to know what this 0.53, the value 0.53 meant. Okay. So how correlated? Or it is yeah, we know it's possibly related, but how we can use this degree of the R value. Okay, so R value itself doesn't have much things to say because of a cumbersome of the standard deviation as a unit. The better way to use R value for interpretation is use the squared value of R. Okay, so make a square the value of R, like 0.53. So square the value of R, R five. So point maybe about 2% or something like that. That R square the value can be interpreted as how much percentage of the changes, how much variability and variance changes by another variable on the other variable. So just going back to the example that we used. For example, the temperature, the weather really impact so R squared the value, let's say, is zero point 0.3, okay, then we can say that 30% of the beverage consumptions can be explained by the temperature changes or temperature. And that's geographical location, whatever the hypothesis you're measuring. So, how much variability in changes that can be explained by another variable? That's how you can use R square values for interpretation. Isn't that neat, right? So I already explained that R value, when we have a T score, right, from T tests, you can calculate R value. That's how much they explain. And that we sometimes use R square value for effect size. Okay? What about meta-analysis, aggregating all quantitative research out there, they use R value and R square value for the meta-analysis value for their research paper. Okay? That's the interpretation and more intuitive interpretation you can make. Okay? So now let's move on to linear regression. Before we move on to linear regression, is there any question about correlation test? No? Okay, it's clear? Okay, great. Linear regression is you can think about linear regression model as a sort of extended and I do not want to say better, but it can be more sophisticated approaches than correlation test. And also, uh, regression model can tell you more out of it, more out of the test than correlation test. Correlation test itself, it just say how much and how strongly and what way they are related. But regression test, again, depending on your hypothesis, you need to decide whether it's a correlation test or a regression test. But purpose of regression test is still the scalable measurement for the two variables are both are integer and quantitative and numerical variable. Same thing. Okay? But when I say more, what is a more? Okay, here we go. So both correlation tests, regression tests, looking for is a better way to see whether those two integer variables are linearly related. Okay, both the correlation and regression model looking for that information, and also both the correlation and linear regression model really dealing with the two integer variables. Okay, so out of regression model as well as the correlation model, we can tell whether there are some sort of relationship going on. It's positive or negative, how strongly they are related, and whether those relations are, linear or non-linear. If it is a strong value, their linear relationship is strong. But it is not strong, maybe it's not totally linear. Okay, so we can tell the form of relationship. Then, beyond the correlation test, that correlation cannot test, but regression model can do is causal relationship and equation. That's the beauty of regression model. So regression model, beyond the correlation model, we are now testing based on your hypothesis. Now we know what is independent variable, what is a dependent variable. So we know causal relationship. Then it's a regression model. And also we wanted to come up with some equation model. Okay, equation model that in the future instance we know an x and y variable. If we plug in those value, we know the final outcome. So if your purpose is to provide a certain equation model, then regression model beyond correlation model. Right? So here for the regression model, I want you guys to have some sort of, we want to be all on the same page in terms of notation. Really, the correlation, I'm sorry, beyond the correlation model, regression model, we are doing is to make sure we have an equation model, something like this. This is a simple regression model equation. And if you have a multiple regression model equation, then you simply go multiple independent variable. So beta x, maybe plus beta 2 and x2, beta 3 and x3. So if you have a more than one independent variable, it's a multiple regression model. But just for this week, let's stick with the correlations and the additional information we can get from simple regression model. When I say simple regression model, it is regression model with one independent variable and one dependent variable, both are interval. So y variable in the regression equation model is dependent variable. X variable indicate independent variable. Beta That is the notation for the population slope. And alpha, that is okay, it's different from the alpha value and alpha level for the critical region, but it's a different kind of alpha. It's a baseline. Whatsoever we do, like voting, whatsoever we do in terms of age, it should be at least 18 years old. Baseline. We started from 18, right? So that's alpha in the regression model. So the purpose of regression model is to find this alpha and beta value so we complete the equation model. That's a regression model. Okay? So just simply y is a dependent variable. Also those baseline, we say y-intercept. It's a baseline. If nothing is happening and there's no independent variable at all, what is the baseline? That's y-intercept. So in y and x axis, where that point hit on the y-axis. Okay, so that's y-intercept. That's another term we can use. So this is equation model, but in reality, okay, in order to make equation model, you need to understand there are a lot of errors comes with it. Okay, this error is the most crucial part of a regression model. I will tell you why. Okay, I will tell you why. You know, 2, 3 slides. Okay, so let's just talk about slope first, which is the beta that we want to represent for the population, slope, right? So in equation model, the beta is the slope when x variable, independent variable, changes by 1 unit. How much changes in a y variable? How much changes in your dependent variable? That's beta, right? And then here in the graph, when that hit in a y-axis, that's alpha, the baseline, where it starts, right? So that's what we need to find for regression model, to find the alpha value and beta value. So when you look at the regression model, so just a guess with this information. Okay, this information. So when we have some units like it goes like that, for x variable, the units goes like that. For y variable, see when you hit those the y axis, that's exactly what the alpha value stands. And then the signs of slope, negative here, negative 16, positive, it's a positive 25, it's a positive and a positive 8, right? And then you just see some degrees, right? But the biggest difference is between a slope in the regression model, it's really raw slope, not standardized the slope like a correlation value. So the value of the slope can go not like in the range of -1 and +1. It can go as much as large as small as, depending on unit of analysis. Okay, depending on unit of analysis. That's the slope, the raw slope. That's the slope we use for the regression model. So the slope in the regression model can tell you whether it's a positive and negative. Okay, but we cannot tell how strongly related. Okay, because it depends on the unit of analysis, right? If it is the unit of analysis is wider, maybe the slope is a steep, it's a flatter, and the units are tend to be, I'm sorry, like it's wide and it's gonna be more condensed, the slope can be steeper. Okay, um, it's a smaller increment that goes on for each y and x variable. The steepness can vary by the actual unit we use for the measurement. Okay, so we can really tell the strength of a relationship out of the raw slope from regression model. right? So in order to test it, there's a way we can do. We can force these slope to be our value is standardized slope, and we can compare that. But we actually do not like to do because, especially when we do multiple regression model. Let's think about age, I'm sorry, age and income. Okay, age, the unit of analysis is a year, and income is a dollar or $100 or $1,000. It's a totally different unit, and then you try to standardize them. It's forcible. It's not natural, right? So we don't like to make this slope standardized and compare, but we just use as a raw slope, and it actually can be uh, very useful when you make interpretation, okay, later with the result of regression model, because the unit itself is intuitive. So for example, $10,000 changes in your income will change how much in your like a social well-being, or how much leisure time you have. So it's more intuitive rather than what we try to do, make interpretation with a correlation value. So again, the slope for the regression model just depending on unit of analysis and nothing to do with the strength of a relationship. Okay. So as I mentioned that the purpose of finding regression, equation model is finding the value of alpha and beta. Okay, but basically using sample, we say A and B. That's the value from the sample, but eventually replace equation model. That's we estimate as the population value A. Uh, I'm sorry, alpha from the A, beta from the B. Okay. And then regression model, and you may read from many academic research paper, it is a least squared method. Least squared method is a regression model. The same thing but different term. Why? Because we select and choose a value of A and B at the least squared value where we minimize sum of squared error as the minimum. Okay, as the minimum. Okay, I will be back to this slide, but let's look at this one first. Okay, I actually got it from the textbook, so no worries, you do not need to throw. So let's see, this is a regression model line. Okay, this is a regression line. It's a perfect, but in order to draw this line, okay, we need a value and we need the slope. But there can be multiple regression line you can draw. But where we can draw line like that, line like this, and some are steeper and more flatter, you can do hundred of different line, okay? To just meet with some of those observation. But where you gonna fix alpha and beta value, A and B value from the sample, where, I'm sorry, where you, when we aggregate, what we call this, it's error. Actual observation value is here, but actual regression line is here. In order to meet everybody's, the tendency, and actual value is right here, but the regression line is actually right here. Whatever the line you draw, when the aggregate values of all error term, all the deviations, when it is the minimum, that's where we draw the regression line. So that is why we call this method of least squared. So where we fix A and B value, where we minimize sum of the squared error, get to the minimized. That's where we fix the regression model. So if we are, if you read academic paper, it said that the least squared model, that means it's a regression model. Okay? All right. So where we minimize it. Otherwise, you can draw as many as arbitrary line that you think is prettier or steeper, right? Where these are all summation of the errors are smallest, that's where you're gonna put A in the slope value. That's a regression model. Okay. So where scared the error as the minimum. By the way, as in the textbook and some other academic paper, when you see y hat, that is a regression model. Okay, it's estimated model and regression model. It's not really perfectly meeting with the real data, but estimated model at our best, best way. So sum of a squared error, where is the minimum between the actual observation and the actual regression line. When this information and summation of that is a minimum, that's the point that we're gonna fix in A and B. Okay. Then I wanted to make sure that you also, again, it's a non-numerical assumption. It's not really somehow your samples and your data doesn't really fully support it. There's a way we can forgive that. But theoretically, in order to draw, in order to draw the regression line, we wanted to make sure, for all the possible x variable for, x values of, for example, 3, around that, okay, there's a certain point it crosses with the y variable. We fix some values right there with the regression line. We wanted to make sure across all the regression line, the variability, okay, for each variable, they're similar. Let's say a certain point in the regression line, maybe in x value of 5, for example, the variability is huge. And most of the variabilities are like around the regression line, but it suddenly get wider. It doesn't really intuitively appropriate, right? So we generally assume along with those changes with x variable, the variabilities are similar along with the line. And then when we fix those line, we hope the line just is like a most probable value of the line. So around those regression line, the distribution of each values on dependent variable, they are normally distributed. So that's a peak of the normal distribution. So it is intuitive that, oh, this regression line mostly touched the best possible value for that specific value. So those are assumptions, okay, theoretical assumptions we have. Okay. So for hypothesis, um, null hypothesis is again slope beta to 0. An alternative hypothesis, depending on your hypothesis and how much theoretical understanding you have, whether it is a two-tailed test or one-tailed test, or it is a directional hypothesis, you can write down. So for two-tailed test, whether there is a causal relationship between your independent and dependent variable. And if you know by theory, we know it is a positively related, or whether it is negatively related. You can write up. Okay, beta is negative side, beta is positively related. You can write up, different alternative hypotheses for your own purpose of the research. Right? So let me briefly go over. It's simple enough, and I will stop. It's gonna be the last thing I want to cover, but it's not full uh, completion of a regression model because I want to leave whole equation models, a statistical analysis, and the statistical value. Uh, it makes more sense for us to talk about whether that equation model is statistically significant or not. We use F distribution and F test to determine that. And for the whether slope is statistically significant or not, we use a t-test to run it. Okay, so regression model, we use two tests. T-test for each individual slope for each individual independent variable. But once simple regression model, if independent variable is statistically significant, then the whole equation model will be statistically significant, right? But in multiple regression model, variable A, independent variable, variable X is statistically significant, but second independent variable can be insignificant and third independent variable significant again. Then we wanted to know whether this equation model is worthy. It is statistically significant or not together. That's F test. So I want to leave those equation model together, the whole equation model statistical significance for the discussion for the multiple regression model, which is the topic for the next week, okay? But at least for each slope, we use a t-test and how we do that. So t distribution and t-test, we actually plug in and put slope, the value, row slope value as a numerator, and the standard of the slope across the slope, what is the changes and variability standard error of the slope as denominator, whether the slope itself had a distinctively larger information and some trend compared to the error. That really determine that it is statistically significant or not. Okay, so we use T statistics using, again, it's just the foundations of statistics. What we want to measure? We want to see whether slope is significantly important compared to the error of the, based on the samples, actual score, and observation. Based on those error, considering those error, still there's a certain patterns for the slope. That's what we are testing. Okay, so that's the t-test and t-value we're gonna come up with to determine statistical significance. But here, for the t-test, in order to read the t-table, you need to have degrees of freedom, right? Degrees of freedom really determine the statistic value from the t-distribution table. But here, for the regression model, can you tell me how many values we actually fixed? So what can be the degrees of freedom? We actually, for regression line, in order to draw one line, how many points we need? At least two, right? So if we had the point here and point there, we can draw the line. Okay, the same logic. We fix the value for alpha and beta, or from the sample value of A and B. Once it fixed, it's a regression model, equation model. So degrees of freedom for the denominator for standard error, we find the degrees of freedom is a sample size minus 2 because we need the A and B value to fix the line. Okay, so that's the some of the theoretical argument statisticians said for the regression model. Okay, so I will stop here today. All right. So once you are back on Thursday class, I will show you how to run correlation model and how to run simple regression model and what additional interpretation, what additional information you can get out of a regression model. But again, it goes back to your hypothesis. If you don't need a summable equation model and causal relationship, you can just simply run correlation model. Okay, so that will be the practice we'll do on Thursday class. But as I mentioned that in the beginning of class today, bring your own variables so I can help you one-on-one, one-to-one to go over, because the due for the next project, next data cleaning process, and you should submit for me to confirm that's next Thursday. So I wanted to help you with that on next for the rest of the class for the lab session. Okay. Otherwise, have a great afternoon. Again, I really appreciate your insight about some current matters and current issues. And I think as a graduate student, you should have some insight what's going on. To not really read and observe what's out there. Just I think you need to understand, digest information, and get more valid information and understand with a better standard and value and logic. Okay, so I appreciate that. Okay, all right. Otherwise, I will really let you go and have a great afternoon, and I will see you on Thursday.
Awesome. Thank you.
Thank you.
Thank you, ma'am.
Thank you, Rahul. Bye.
Thank you, Sam.
Thank you.